Okay, this talk is about abstraction, but before we dig into that, I want to start with a demo to anchor the discussion. This is a virtual scroll component. I haven't added very many records yet. So first we have a t-shirt orders table. We have an ID, an email address, and then we have the gender, and then we have the shirt size. And the shirt size has a pick list, and there's a dependency on the gender. So if you are a man, you see men's shirt sizes, and if you are a woman, you see female shirt sizes. And also the pick list is filterable through the type ahead. And this filtering happens on the server because what if the pick list has thousands of items, right? A high performance application that has to happen on the server. Let's also add a bunch of data, 1,000 records. I just reset the reference, so I need to refresh. Okay, so now we have a virtual scroll. And this app is built with Electric v3. So let's look at this virtual scroll. So we have TRs in the DOM, and only the TRs that are visible are there. And as I change the viewport, over the network, remote server dependencies are streaming in. And as I unwind it, you can see things are removing from the DOM. So we are responsive to the size of the viewport, and the network is also responsive, not just the rendering. We are streaming in records from the server in real time as we do this. And then there's also, you can scroll it and the cells scroll in when it as the scroll offset changes. And even throughout all of this, like the pick lists still work, right? The central question we're trying to ask with Electric is, what is the simplest possible code we could write to achieve this? So this is not the code for this demo, but it's a good enough starting point to look at. Like, look, it's very straightforward code. You have a query, you have a table, you have a for loop, you render to the TR, and you have a row renderer. How could we refactor this so that you don't see any of the details of this responsive network in your code? How far can we get in terms of pushing this kind of abstraction? And we call this network transparency, when you can write code that is transparent as to the network IO happening in your program. So network transparency, I have a definition, is the ability of a protocol to transmit data over the network in a manner which is not observable, transparent as invisible, to those using the applications. Okay, the users may access remote resources in the same manner in which they would access their own local resources. Okay, and that's what we're trying to accomplish here. There is a dependency on a query, and maybe that query is on the client, maybe that query is on the server, but we want to write a generic component that is agnostic to it. It just doesn't care. It is transparent as to where this query is. You can see no difference in your code. Okay, so as an agenda, we've already done the demo. I'm going to tell you what Electric is for, what motivated us to build this. We're going to do a quick tutorial. This will take 3 minutes. This is to help any beginners or newcomers to Electric get caught up very quickly. And then what we're going to do is we're going to build that virtual scroll, highlighting the Electric v3 upgrades that make it possible. And we're going to do this in a series of refactors, of 4 refactors. And that's the talk. While we do this, we're also going to over and over have this theme of differential data flow, which is, what is the computational structure that allows you to have this reactive streaming network? In essence, you want to have a collection distributed from the server to the client, and you only want to have differential updates, diffs on the wire from database to DOM. So that's the theme. Okay, let's start with the motivation. We are trying to make applications that look like this. This is a business process application. Is built in Electric v2, and it has fixed tabs. It has fixed queries. There are a set number of queries. It has tons of static structure. There are fixed widget types. These pick lists are all the same. You have the same queries in each column. There's progressive enhancement, but even like the yellow spots, it's statically known. The only dynamic structure that's visibly obvious is the number of rows in each table, right? So it seems like declarative programming should be a natural fit for this. But the problem is, this structure has operational runtime requirements which must be met, specifically the network performance and the rendering performance, okay? At the leaf node, inside these cells of the table, there's a pick list, and that pick list, as you saw, may have a sibling reference or have some complex business rules. And the pick list is only loaded if you click on it. So there's an if statement in that pick list. There's control flow where you have to make decisions of whether or not to load something from the server. And this breaks any declarative abstraction you can build, because there is control flow in every leaf node. Therefore, the computation as a whole is not actually declarative. It is dynamic. it has control flow, you need closures. So you end up needing global coordination in real world apps. And that basically frames the problem of what we're searching for with Electric. What is a composition model that allows you to have control flow and business rules at every point in your program, but also be able to compose with respect to networks? You don't need central coordination at the top of your program to like the programmer can inject knowledge for how to optimize this computation. How can you make this fast in a way that's truly composable? So this is what Electric is for. What Electric is not for, it's not for websites. Electric is for rich web experiences. So we do not server-side render. It's not on the roadmap right now. We're good for visual programming tools. They're real-time, they're interactive, they have rich network connections, and it may not even be feasible to code those network connections by hand. An example of this would be Cognitect's Rebel project, which in order to work around having to code these network connections, they made it as a Java Swing GUI desktop application. And due to this, the project doesn't really swim. It needed to be done on the web. Okay, so it's for rich web experiences. Electric is for experts, not beginners. Electric is a very sharp tool, as is Clojure itself. We do have lots of beginners succeed and successfully make applications with Electric because Electric is bringing things within their reach that was not within their reach before due to all the complexity of React.js and that ecosystem. However, we made Electric for experts, and we are not apologetic about this. There's a learning curve. And finally, Electric is for business process apps, not just user tools like this. The key thing about these is you care about rapid prototyping, development velocity, basically cost and schedule. There is jank as we still continue to iron out the kinks and make Electric better. It is not necessarily a good fit for like pixel perfect consumer applications like Facebook. You might be frustrated. It might take a lot of internals knowledge to make a perfect app, but we are getting better every day. And in the meantime, internal business applications is a great fit. We're good for that today. Okay, for those of us who are joining us for the first time, I'm going to show two quick demos. This is our, in V2, a database browser built with Electric V2, and we are scrolling over 10,000 records. And what we're doing is we are streaming thousands of records from the cloud all the way to the DOM in a way that has absolutely no perceptible latency. This is done in Electric V2, over 10,000 records. Okay, we also have 2Do MVC. Electric is a full stack paradigm, so it's actually reactive 2Do MVC. It's transacting to a server database and storing it, and then the queries refresh and fan everything out. And of course, you can do styled applications in Electric. And then finally, here's an example of a visual programming tool. This is a robotics, industrial robotics observability UI, where you have, this is a shipyard crane loading fish meal into a boat. And we've recorded a log of the crane into this playback UI, and you can see we are streaming events from the robot log to the UI at 20 hertz. And then what's going to happen is like you can jump around and you can like increase the playback speed. Here, I'm changing the playback speed and like fast forward. And now it's not 20 hertz. Now you're just streaming like a huge amount of data. And you have this big collection in the DOM, and React.js can't even handle that. You need to maintain the collection, stream in stuff from the right, and then evict DOM from the left and do this efficiently. So Electric is a good fit for applications like this. Okay, that's what Electric is for. Now let's do the quick tutorial. So you've seen this before. This is the 2 clocks demo. It's been upgraded for Electric V3 this time. The easiest way to understand Electric is its streaming lexical scope. So we have a clock on the client, a clock on the server. We're subtracting them. Here's the client clock. Here's the server clock. And you can think of CNS as a stream of values from that clock. But you can also think of it as like the latest value from the clock, because when you go here, we auto map the minus sign across these asynchronous streams of values. So you really get the subtraction of the latest values. And because Electric is auto mapping this function over the asynchronous types, it feels like nothing is reactive at all. Okay, the types cancel out. Technically, this is a signal asynchronous type. It is not a stream, but not everybody knows what a signal is. So when I introduce Electric, I tend to use the word stream. For the rest of this talk, every time I use the word stream, it's actually a signal. Okay, eClient, eServer, these are compile time markers. edefin defines an electric function. It's a macro containing a full Clojure and ClojureScript analyzer. It compiles this Clojure syntax down to Clojure and ClojureScript target code. So that means that runtime, there are two processes. There are a front end and there's a back end, and they communicate by WebSocket. $ is in V3, this is the function call operator. In V2, we used object syntax, and there's a couple subtle issues with that, so we're not sure if we're going to keep it. For now, we're using $. Electric is Clojure compatible, so you can't use regular application syntax for electric functions because we need to differentiate. This is a Clojure function call, and this is an electric function call. Both front end and back end are reactive. When this reactive clock fires, we build a reactivity graph and we look for the downstream dependencies. So the clock ticks, it's needed here, which is on the client. A message goes over WebSocket, and then you rerun this subtraction function, and then you update the DOM by point mutation. DOM rendering is effectful. So when this updates, you get a point right here to this position in the DOM. The DOM knows where it is in the AST. There's no virtual DOM, there's no React.js on the page. Electric is already fully reactive at the programming language layer, so there's no need for something like React. If you do want to play at the functional reactive layer and use the asynchronous types and not have the auto mapping, there's a trapdoor to do that. In fact, this clock, I don't want to show it, but it's implemented using Missionary, which is a functional effects system. It lets you drop down to this concurrency layer to implement an efficient back pressure clock that only ticks when you're looking. Okay, so low-level concurrency control at every point in the computation is a first-class feature with Electric. All right, with respect to Electric V2 versus V3, nothing has really changed that you can see here. So I'm going to go on to the next demo. I need to clear out the database so there's not thousands of records. Let me reset the database. Okay. WebView Concrete. Okay, so what's happening here is we have a database query returning the t-shirt orders. We can filter it. We've got the two pick lists. There's a sibling reference between the pick list, and the pick list is filtered on the server. Let's look at the code. This is the entry point. We're binding the server, the database on the server. This is a data script, but it's on the server. The search is this DOM input on the client. Notice that you have a let statement with both a client expression and a server expression in the same let. This is a new feature of Electric V3. When you assign a symbolic name to something that's on the server, you don't want the act of naming it symbolically to cause a network transfer. You just want to say, hey, this DB is this expression, and you want to be able to like pass that expression around without actually transferring it unless it needs to be. So that's possible in Electric V3. You have the database on the server, the search on the client. We pass it through to this electric function. So here, search client. The values pass through without transferring over network. About this let statement, because this is on the server and this is on the client, these two expressions must run concurrently. This expression is running on the server, on the client. That's two different computers in two different areas of a distributed system. You couldn't make them run in order if you wanted to. So that means in Electric, let statements are concurrent as of V3. This is a departure from Clojure semantics where let statements are ordered like statements. They run in order. That means in Electric, if you put printlns here, they're going to happen concurrently and they will race. Okay, so we've passed the database on the server, the search on the client, server client. They pass through to this query. So this is the t-shirt orders query. Here it is, server, client. The sort key is optional, it's nil here. And let me make my window bigger. Okay, so we're on the server. I'm going to do this from right to left. This is the blocking database query, the data script query. This is on the server. This is on the client. This Clojure interop is the reason this search input, the string from the client, had to go to the server. Just naming it or passing it through an electric function does not transfer to the server. The thing that forces it is you have to pass it to Clojure, and this function is running on the JVM, so you need this on the server now. What offload does is it moves this function to a thread pool because this is a blocking database query. It's potentially slow, and electric, even on the back end, is a reactive computation. It's asynchronous, so we don't want you blocking the asynchronous computation. You have to offload your slow queries. Let me make it a little bigger. Diff by. What this is doing is your t-shirts query returns a collection 9, 10, 11, and as you filter this, like the collection result changes over time. So what you want is a way to stabilize this collection in the DOM like this. So as we filter and this query result evolves, we need a way to correlate it so we know that row 10 corresponds to this element in the DOM. So what we do is we use diff by. What diff by does is it separates this collection and isolates it down to individual elements, calling identity on them to get the key, the identity of that item in the collection, so we can stabilize it all the way through. So essentially what you get right here is a stream of diffs saying the change set of this query since the last time it ran. Okay, that means here, this is not a collection. This is a stream of diffs. The for will materialize in the DOM, the collection, statefully based on the stream of diffs as they flow through. That means in the DOM, we have the 3 rows here. This is the only place in your application where you can see the collection be materialized. The collection is not materialized here. This IDs is not a collection. This is a change set. So that means you might ask a question. Is this well defined? And the answer is no, it is not. Why? Well, the problem is IDs is a stream of diffs. So reverse takes a Clojure collection and it looks at each element of the collection in order to reverse it. So you don't have the collection in memory. You can't do it. What you can do is materialize the collection. What ASVEC does is, like for, it statefully accumulates the collection to materialize it from the change set. In fact, we can now print it and see it in the console. Bob 10, and now we remove the filter and Alice and Charlie come back and we get 9, 10, 11 is materialized. This is not a very useful primitive. It's good for testing and debugging because once you have this collection materialized, like you've damaged fine-grained reactivity, you need to diff it again if you want fine-grained reactivity to the DOM. So really the only thing you can do is diff it back, which is pointless. So this is not a useful operator. It's time to look at the diffs. I want this. So there's this function tap diffs. We're printing the word diff, and then X is an electric value. What we're doing is we are lifting it into a missionary asynchronous type with pure. So we get a missionary flow of diffs, the actual flow of diffs. And then we're feeding it back into the electric program as a value. That's what e-input does. It's an input to the electric program. So what we're going to get is we're going to print the actual diff values now. Now the details of this aren't important. What matters is it works, and we're going to show you. Okay, so to start, I'm going to filter this and remove all 3 items because Q does not match the collection. So what you get here is shrink 3. There were 3 elements in the DOM before, and we've killed all of them, which means this is actually the only information you needed to achieve this. You don't need to have any additional information to remove 3 elements from the DOM when there were 3 elements present. If I continue to type, what you get is an empty diff. Grow 0, shrink 0, no changes. Permutation is how you reflect order. If the database query was to sort, you need a way to reflect order over the network and reorder the DOM. That's what permutations does. Okay. The point of this is you're really getting diffs through the DAG. You're not sending collections back and forth on the wire. If you do this in React, for example, you get a new collection. You need to put that collection into a big JSON document. Then you need to serialize the JSON document, and then you need to pay HTTP overhead to move that document to the client. Then you need to deserialize the big document and all the collections it contains. Then you need to put that into like some normalization framework in order to attempt to get fine-grained updates to your view. And then you pass that to React.js, which is going to render the virtual DOM and traverse the whole collection. And then we're going to pass these React elements to the React reconciler in order to diff them in order to get fine-grained updates to the DOM. That is all waste. The purpose of this diff by primitive is to co-locate the diffing as close as possible to the database collection so that you can have fine-grained differential maintenance all the way through the DAG, all the way to the DOM. So the only thing you can do with this foreign collection is you can diff it. You now have reactivity, fine-grained reactivity, and you get diffs on the wire, and you get O of 1 diff propagation through your rendering all the way to the DOM, where you get a change set diff, and the DOM layer will interpret it and make a point mutation to the DOM in O of 1. Okay. What is this search is a single value from the DOM. What is this? We said IDs are streaming diffs. In fact, in Electric v3, every lexical scope, dynamic scope, all scope is streaming diffs. That means from the input, what you're getting is change diffs as they type into the input. So search also is a stream of diffs. Okay, let's look. So we boot the application, grow 1, and change the value to the empty string. Now, if you think about classic React lifecycle, it has 3 methods that are important. It has mount, it has update, and it has unmount. So if you map that to a diff, grow is mount, shrink is unmount, and change is update. Okay, so we get lifecycle on this value. The difference is in Electric, we also are able to do diffs on collections. So you get permutations, and you also have the ability to have multiple items in a collection. So what we've done here is we've lifted this scalar value into a collection of width 1 right here. So when you materialize the stream of diffs and print it, you in fact get a collection of length 1. Now, this is surprising. No one asked for this to be a collection. That may not make sense. But let's go back to the 2 clocks example. In Electric v2, we said these are our streams of values, and if everything's reactive, nothing's reactive, we auto map the minus over the streams of values, and all the types cancel out, and you can just forget about the types and program as if these are just values. Well, in Electric v3, yes, these are streams of diffs. This is a collection of width 1. This is a collection of width 1. But we are auto mapping the minus over these collections of width 1, and the types cancel out. So you will not notice in your program the fact that these in fact are differential collections. Okay, I see a question in the chat of how do we reverse the list if we wanted to? If you want to do this on IDs, it's basically too late because you've got the change set. So what you want is probably to do this, the reversing in the database before the diffing stage. So if you have like a data layer, your data layer is written in Clojure, this is it. And you diff it at the point where you want fine-grained reactivity from this point forward for efficient distribution to the view. Okay, why is the diff creation explicit? Why do we require diff by separate from the for? In Electric V2, these are actually combined into one primitive for by. We've split this for 3 reasons. The first reason is you only want to diff it once, and you want to diff it as close as possible to the foreign collection, so you get fine-grained reactivity. If you forget to diff here, it's almost certainly a mistake, and you're going to accidentally pay for the diffing in more than one place, or worse, you're going to accidentally transfer that whole collection over network. By diffing it, co-locating the diff by as close as possible to the query, you guarantee that you're going to get differential network traffic and differential propagation through the DAG. Another reason to separate the diff by from the for is because sometimes you don't want to do the diffing because you have like a pre-diff data source. An example of this would be a stream of OpenAI tokens. There's nothing to diff. You've already got the individual elements. Those are your changes, and there's nothing left to be done. So you want to skip the diff by stage. And then finally, the reason you want to separate the for and the diff by is you do want to guarantee that you get diffs on the wire. If you put them together in one primitive, such as this, I'll write it for by, and then here's the react key. There's not actually a syntactical place to put the eServer directive. If you put it here, you've transferred a collection over the wire, not diffs. There's no place to do it. So you really need to separate it like this. And now you can put the diff by here. And now you've got a way to say, I want diffs on the wire. So that's why we did this. Okay, what we want to do next is generalize this because we are trying to abstract. So what we're going to do is refactor this concrete view into a generic table. So here's the original t-shirt orders function. Here is a generic t-shirt orders function. You see the parameters. Here we have a database and a search. We have, those are here. Here's your database. Here's your search. Server client. We have used partial application to pass in a lambda, which is the query. Okay, and here's where we call the query. Similarly with this row renderer, we've extracted that as a function here and injected the row here. The row has a database dependency, so we partially apply that right here. So you get the row, the database. And then we call that here. So here's our generic table. Let's look at the code. So we've got the IDs here. You've got the table that goes here. You've got the for that goes here. And then you've got the TR that's here. And then you're under the row inside the TR. I could show you, but like it's the same demo. Nothing has changed. Yep, demo still works. And note that we've still got the dynamic queries on the inside. So this row rendering function is actually doing complex things. Inside this row renderer, we are switching to the server. We are querying the entity, the email, the gender, the shirt size, and then we're rendering them as a type ahead, which potentially queries for the options. Now, remember, the whole thing is differential end-to-end with diffs on the wire. So I would encourage you to think, like, how would you even do this with another technology? You need like a complex GraphQL engine, and you need to implement all the GraphQL resolvers and worry about the security details and the performance and whether or not you can trust the client. None of that complexity exists here. We have done this in 30 lines, 27 lines of straightforward functional code that anybody can understand. Also note that this table component is sheltered from whether or not this query is on the server, okay? this query is switching to the server to get the stream of diffs from this server query, but there's no server directive here. Okay, so we are attempting to encapsulate whether or not there is I/O so that this table component can truly be generic and work for both client and server-side queries. Okay, next demo. We're going to refactor this a little further. Oops, wrong one. Okay, we still have a generic table, but what we're doing here is we're going to add a column spec. So in an atom, we're storing ID, email, gender, and shirt size. And then we subscribe to the atom, we diff it, we have a reactive collection, we pass it into the generic table. Here is the call spec, it's on the client. And then we use the call spec to loop over it here in order to render the columns conditionally based on whether or not the column is visible. Let's show it before we go deeper. Okay. So this is an atom on the client. My REPL's on the client. And I can swap that atom, and you can see we have a reactive call spec, right? And note, you only pay for the queries you use, right? You only pay for what's visible. So let's see how we did that. The row function here, the row renderer function, returns a map. Let's look at that object. It's a map of the columns, and instead of rendering them directly, we've returned functions that render the cell, okay? So for each key in the call spec, we then get the cell renderer out of the map and then call the function. So you only pay for queries that you actually used and were listed in the call spec, and you call the function. If you don't call those function, no query happens. You pay for what you use. Another thing you can see here is the lambdas are defined on the server, okay? But here, I need to scroll up there. We're calling them on the client. So this lambda, in fact, serialized over network. And I can show you what it looks like due to this print. So this is a lambda. What it is a pointer into the program source code, into the AST, so that the client and the server can agree on which lambda we're talking about and what their dependencies are. And you can inform the other peer that the lambda is in play and has been called, and then they can agree on what the client and server dependencies are. Okay. All right, that's it. We're ready to build the infinite scroll now, finally. So let's, in fact, let's see it first. I'm going to add a bunch of data to the DataScript database on the server. There it is. And let's see it work. You already know it has responsive network, right? It streams in and out. In fact, you can see as I scroll up, you can now see the diffs, shrink one, shrink one, shrink one, shrink one. So there's the differential rendering in the differential network. And remember also, we still have the internal row renderer with the server query. Now let's look at the code. So here's our generic table. This is the generic infinite scroll table. It's got the same parameters, call spec, query, and row. This is browser layout and browser event code. We are using a resize observer to measure the height of the viewport and use that to compute like the page size. And we're also registering for scroll events here in order to find where our scroll bar is in pixels. And we compute an offset and a limit to pass into our query. So we've actually changed the query a little bit to window over the offset and limit. Okay, beyond that, here's the for loop, here's the for loop, here's the TR, here's the TR. We've got some layout props that we don't care about. And this block of code for the dynamic column renderer is copy pasted here. It is the exact same code, minus the props, which we don't care about. So what we are seeing here is, in fact, this virtual scroll with the differential traffic, the diffs on the wire, the differential rendering has come for free out of straightforward naive code. Okay. Now let's talk about the performance. It needs to be faster than this. Let's look at this. I showed you this video. There's lag over Zoom. I don't know if there's lag on this stream, but this is a highly optimized virtual scroll built in Electric V2. That's why it's so fast. If we look at how it works, we are stabilizing the contents of the DOM so that we reuse the divs and we are only writing through the change values as point writes directly into the thing. Okay, so we wrote lots of complex code that you had to think really hard to write in order to get this to be so fast. And we're comparing that to this, which is the most straightforward, naive, direct code you could possibly write. It's just a for loop, like a child could write this code. Not only that, the column, it composes with the column renderer. So here I've removed a column, moved it, right? We got that for free. You cannot see any network related code related to this. We also have a sort key. I've now added a sort key to the t-shirt query. So here's the atom. We're sorting by email, and we watch the atom and pass it to the query. And that's it. Now I can swap the sort key, and let's scroll down a bit. And we get there's a big diff here, permutation and changes. And there it is. It's sorted by shirt size. And now I'm going to order it back by DB ID again. There it is. So this all composed, and you cannot see any accidental complexity related to that in your program. Now let's talk about why this is slow. We believe that this can be as fast as the Datomic demo I showed you. You might assume that this is IO bound. It is in fact not. If I show you the CPU graph, we are pinning the CPU at 100% as we scroll. This is due to a embarrassing mistake. Our electric for loops today, when a single element changes, we are accidentally resampling every item in the collection, which is why the CPU is getting pinned. This is a straightforward thing. Electric V3, we just got working like a month ago, so this is hot off the press. We'll fix it, we'll deal with it, and then this will be faster. The next thing is, I want to look more closely at the network traffic that is happening. I'm going to use the simpler thing to get the scroll logic out of the way because it's the same code. We can look at this. So we know that, where's the query? Here's the query. Due to here, we partialed it, we passed it in, and the t-shirt orders query is running on the server. Okay, so at this point, the IDs are on the server. They're also on the server here. But at this point, the for is client sided. So due to this client site, we've caused a transfer to the client, okay? Which means this is on the client. This is server, this is client. We call the row function, but we need to put it on the server here to query the database again. So this is an accidental round trip. The way you fix this, one way to fix this is to do this. Now if we do the traffic, server, the for loop is on the server. The DOM table macro in Electric V3 is smart enough to pass through the site. So in fact, I can show it to you. Inside the DOM layer, this is the element constructor in the DOM inside this DOM table. Here is the side effects to the DOM. They're all on the client. but we call the body continuation of the table without touching the site. So what's happening here is the E4 is still on the server. So server, 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 and now we fixed the round trip. The reason I didn't do this already is because Electric v3 still has bugs. This crashes. It shouldn't. It should work. It works in principle. But there's still a problem I want to point out, which is that it's not a generic table if you have a site inside of this. The actual abstract code we want to write, which lets us forget about the network, is this. So now what we've done is there are no client or server directives. It will inherit through dynamic scope the site that it's on. The query is called. This is on the server because it's on the server here. The table passes through server, server. Okay? Because we inherited this server site in dynamic scope. The question at this point is it truly abstract? And there is a problem. You have to remember to put this server here because the t-shirt orders query that you injected is also on the server so that the site of the for matches the query, okay? This is a problem. This is a point of global coupling between the call site of the table and the query, which is in a different file. We think we can fix this. What needs to happen is basically, oh, what's that? The for needs to be transparent to the site. It needs to basically keep the ID on the client and the server so that it can pass it through to this server expression without moving it, but also pass it through to like some client usage. So it's in both places. That's future work. But anyway, we think we've done a pretty good job here. This single piece of global coupling is really not bad. And if you compare yourself to like React.js, like it's nothing but global coupling. You have all these REST endpoints and databases and you're optimizing the EIO and like the whole thing is one good big mess of global coupling. So this is pretty good. The consequence of you forgetting this server block is you'll have a slower program because of this spurious round trip. A FAQ is, how do I remember to put the server there? If you think about the data flow in a web app from as it moves through the client and the server, in the view rendering phase, it's always pushing data from the server to the client. We're distributing data to the views on the client. So generally what you want to do is just bias everything to the server. Make this on the server, put everything on the server, switch to the client when needed, and you will out of the box have a fast app because always everything is going server to client data flow. Until the interaction phase where the user interacts, and now it's opposite. The event side would be server to client. But most programming in web applications is about the view side. Okay. We'll take questions in just a minute. We're wrapping up. This project is funded by consulting. Electric v3 will be stable in about a month, at which point we'd like to partner with a funded revenue generating team to see how far we can push this in the most complex real world scaled up application we can think of. Our sweet spot is internal business applications like this one I showed. This is built in Electric v2. We'd like to build an app like this in Electric v3. We can build apps like this incredibly fast due to these abstractions. The Hyperfill product also, we are building declarative DSL that can basically do this in even fewer lines of code powered by Electric. That's also open source. Visual programming tools like the Robotics Studio is also a good fit. Is it ready? What's good? What sucks? Performance is fine. Like this performance here is probably better than the GraphQL or REST thing that you're doing with the pagination, right? It's fine. And it's going to get better fast. We need to fix the CPU bug, and then we need to fix the crash, preventing me from putting the thing on the server and limiting the round trip. In principle, Electric v3 will be faster than Electric v2 due to using a better algorithm and data structure. We just have to do some optimizations. There used to be a disconnect issue in Electric v2 where if the WebSocket was interrupted, the client would shut down and garbage collect all the DOM and turn the page white. That is fixed. If the WebSocket goes away in v3, the client application will continue to run and it will gracefully resync when the server comes back. Flicker, Electric v2 had a flicker issue. The thing causing the flicker issue is fixed. As you can see, this does not flicker. Part of the key is a fixed layout. When you use Electric, because everything is concurrent in racing, the order in which things are written to the DOM is undefined, and you want to have a fixed layout so you don't have layout shifts if a longer string comes onto screen and causes a column, an organically sized column, to be wider. When can you use it? We are releasing an unstable preview of this week. To get it, you have to ask, DM me on Slack, and I'll add you to the waitlist. We might require you to do a Zoom onboarding for a few people. And team. Electric is the work of 4 people. The differential structure of Electric v3 is the work of Leo Noel, who is a French concurrency researcher, and in my opinion, the best in the world in our space, as you can see from this design. In addition to Leo, Electric is the work of 4 of us: Jeffrey Gaillet, also representing France, Peter Nagy from Slovakia, and myself. Each of us has made deep and substantial contributions to this product. And to my colleagues, it has been the privilege of a lifetime to work on this with you.
Simon is asking, I'm not sure if it was answered. What happened if you try the reverse without the asvec?
There's something I can show you here. Do we have 5 minutes?
Sure.
All right, this is cool. The question is, we know this doesn't make sense because this is a stream of diffs, and this is a linear operator that needs to see the realized collection. So that doesn't make sense. How about this? Like, this should be a type error because you have a change set. Like, how do you even give that to Clojure? And then you're inking it. In fact, let's start with something simpler. Tap disk search. Print asvec search, and print search itself. This is a new thing. I didn't show this on purpose during the talk. So we have 3 things now. Before we look, I already told you that in Electric v3, everything is an incremental sequence. So this is obviously a stream of diffs, but the search from the input is also a stream of diffs. It's a collection. It's a differential collection of width 1. So when we print this, you're going to see, let's do it. Oh, I'm in the wrong demo, and I need to shrink my database down to size so it doesn't blow up on the server. Rec view concrete. Sorry, Electric v3 is unstable still, so I have to refresh a lot. Did I fail to clear my database? Oh, I think I added even more stuff to the database instead of killing my database. Setup DB. There we go. Okay, so let me reorient. So we've got search, which is a single value, but it's as a stream of diffs. And when we print asvec on the search, we get the singular collection, a collection with 1 element. And remember, we're auto mapping this so you don't see it. So if you look at this line, print search, it's actually here. What we're doing is we're auto mapping the print across the collection of width 1, and you get a single print. Okay. So if you look at the diff, like, there is enough information to do that. You need the empty string to print, and here's the change. You got a change instruction, and the list has 1 element, and the 0 index is an empty string. As I type into this, right, you just continue to get the changes, and you continue to get the empty string. So where it gets mind-bendy is, let's do this for IDs. And here we have something very interesting. Oh, no, I want to do this. I guess I have to do this. That off the top of your head would seem like nonsense. Let's see what it does. So I'm going to start with Q. This is a diff that retracted everything. And now I'm going to delete it to bring everybody back. So we got a grow 3, Alice, Bob, and Charlie. And what happened here is we auto-mapped the ink across the change set. Okay, so this is shocking. You didn't see any of this in the talk, and that's on purpose because this is a product. No one asked for function application to blow up in products and map across the change set, right? It could be an exception. We could absolutely say, well, you can't do this, right? It's a collection. It's not meant to be a value. You can't call link on that. Can't call anything on it because you don't have the full collection. But it is well defined because you have the changes in the change set. Like you have the individual elements, and you can do something. It is well defined to call the function on the change set. So essentially, the fundamental structure in V3 is we say, what is diff by really, right? We said it's a stream of diffs. What it actually is, if you studied SICP, is it's returning amb. Amb is, it returns a list of values in superposition. This is returning 1, 2, and 3 all in superposition, and therefore you call the ink on each one. Okay, so in electric, amb is a diff constructor. It's a differential sequence constructor. What diff by returns is it breaks up your elements 9, 10, 11 and returns them in superposition to be auto-mapped. And you put this, IDs is the collection in superposition, and then the 4 will isolate them down to a single one for your syntactical convenience. So I'm going to start doing some tricks. What is this? It's a product. 20, 10, 1, 2, 3 by 20, 1, 2, 3 by 10. Okay, call the vector for the product of these two things. It auto-mapped it. Okay, what is this? There's the sums, there's the products. Okay. What is so now we've got Alice, Bob, and Charlie vectored with 10 and 20 as a product. But remember, it's a change set. So what if I filtered down to Bob? What we've done is we removed Alice and Charlie from the graph. And what printed? Well, nothing printed. We unmounted some of those vectors. We unmounted any vector that touched Alice and Charlie. And if you bring it back, Alice and Charlie just came back, grow 2, 9 and 11, and you got the product on the change set. Okay, it's a differential product, change set. So you could think of this as the vector unmounting or mounting. If it was a DOM text, you'd be mounting or unmounting the DOM. So it checks out perfectly. And it turns out this is an extraordinarily valuable primitive. This is nothing. This is the empty diff. You've now multiplied your function by 0, essentially. It will not be called at all. This is a way to pause the computation. In Electric V2, we had a pending exception, it just caused all sorts of problems. And we just wrote macros to silence the pending because it was causing chaos. Amb is now pending in V3. When a computation is pending, it returns amb and it halts your program until the amb has more elements in it. And then finally, if you have a for loop, we have a problem because this for loop needs to accumulate up a collection, right? If your DOM TR returns nil, you're going to get a collection of nil, 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 nil out this for loop. and it's eventually going to go back to the server, and you need to send it to the server because someone might depend on that on the server. So you end up sending collections of nil, 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 nil over the server in Electric V2, and there's no way to stop it. What you actually want to do is have the DOM macros return eamb, and now the for will flat map it, and you get a nothing. You get nothing out the top. You get an empty diff, which we won't even bother to send to the server. So you do have to have this to have efficient UI. Okay, I'll stop there. That's probably too much.